Hi, my name is Mike Look. I'm here to talk to you about AI, what it is, how it works, and what the future of AI can bring. Over the last 80 years, what's really driven the advancements in AI are really three things. The quantity of data available, the advent of the internet about 30 years ago, exploding the number of web pages, the documents, and also the number of images even available has obviously increased dramatically. So that amount of data that algorithms can learn from. The second component is the algorithms themselves have advanced tremendously over the last 80 years as well, with things like neural nets being developed in the 40s, and then support vector machines, decision trees, and then the last piece of it is just the amount of compute and the capabilities of our computers to churn through that data and to learn those patterns. And so there's a famous Moore's law that exists for transistors, where the number of transistors on a computer chip will double every roughly 2 years, meaning that you can churn through more and more data. You can learn more and more of those patterns with more and more sophisticated algorithms that exist, allowing us to have better and bigger models in AI. To allow more complex tasks and more complex reasoning to be performed by computers. And then we move into what are the components of AI, like what actually is AI? So there's three things I like to think about how AI works. The first is what type of sophistication of AI that we're talking about, what level of AI. The second is the data sets that they learn from, like what data modalities, and I'll talk about that. And the last one is how they learn from that data. So how the AI algorithms are learning from that data set, right? That learning paradigm. So starting with what types of levels of AI there are. So as I mentioned, AI as a broad term is basically the ability for computers to imitate human reasoning and human logic, be able to perform tasks. Within that, there's a subset called data science, which is geared towards doing that, but in a data-driven method and data-driven manner. All these are set equations that have empirically been shown, and you can sort of like program them in manually, right? And have like some software engineering background and like start programming it if else clauses and those kind of things that allow you to perform things with the data and driven by the data set. Going into the more advanced ideas of machine learning and deep learning. So machine learning is now going into a field of, it's really a suite of algorithms and methods that learn patterns from data. A generic set of algorithms such as support vector machines, decision trees, and those kind of like paradigms that allow you to just ingest human parsed features so that it can do things that are useful. One step further in complexity is deep learning. And so now we're thinking about things not learning from like human engineered features, but really towards just raw data. And what I mean by that is instead of trying to predict, say, house prices from the number of rooms or the square footage, we basically just take a photo of a house or maybe a document about the house. And you can start thinking about like, if we just give it that data, then algorithms in deep learning are able to learn patterns from that raw data set and say like, oh, these colors are more expensive or more like correlated to more expensive houses, or these features or these curvatures are more correlated to more expensive houses. And so again, it's mapping from that more upstream data set of like raw data all the way down to the house prices. And so that kind of idea allows us to build like internal representations of how these algorithms are thinking about data sets. Beyond that, there are a couple more different subsets of AI. The one that's more relevant these days is Gen AI. Generative AI is an ability for algorithms now to so well understand the data set that it can start generating new content. So you can model the data set and model the data that you train on in such a way that it has a firm understanding of like the shapes and distributions of the data set. And then now you can start generating images that are similar, generating pictures of houses, generating pictures of cats or dogs and those kind of things. So for example, in machine learning, this is when it's trying to learn from raw features. So for example, if a real estate company wanted to predict house prices and take in historic information about house price sales and like trying to predict house prices, you basically take it in from raw feature sets that are human developed. So you can think about things like the number of rooms, the square footage, where it's located, and basically mapping that to the house price that it sold at. So that really was to do with the sort of like level of AI and the types of AI sophistication. The next major component of artificial intelligence is the data that these models are learning from. And the data sets that exist within companies and within organizations and in the world really come down to maybe 5 categories that I like to look at. First of all is tabular data. So these are things like in your SQL database, in CSV files, and Excel files. So almost every major company in the world will have tabular data sets from which you can build use cases from to build predictive analytics for house price sales or anomaly detection of like fraud detection. If we're trying to monitor for for credit card transactions, those kind of things. The next major bucket is in time series or signal processing. So these are things can range from anything from monitoring EKGs or like heart monitors of your pulse to make sure that you don't have heart arrhythmia, or even things to do with forecasting stock prices. So anything to do with sort of like signal processing where it's like very sequential and time related is another big aspect of data science and AI. The third major data modality is text. And the majority of the internet is text-based, and you can think about doing sort of use cases that are based on anything to do with text, such as maybe sentiment scores for movie ratings that are published online, or being able to analyze sophisticated like financial documents for like insights or mine them for different categories of numbers or statistics. So that's a huge major area where a lot of organizations and a lot of just everywhere worldwide has a lot of use cases towards those. Fourth one is towards images and video content. So learning patterns from, say, how to predict or how to define like cracks in piping if you're running like some QA process through manufacturing, or trying to determine the roof insurance cost based on satellite images, or maybe crop forecasting based on like satellite images of a field and field colors and those kind of things, right? And so there's a lot of space in the image modality where you can build a lot of value from like sort of analyzing the patterns in images. And obviously you can get into like generating of images and generating of text, where you can build and generate like cat images and like cat memes and those kind of things. And again, one of the hugest and biggest data modalities out there. The last one is graph and graph interactions and relationships. So this is a little bit niche and exists really maybe in just certain situations where the relationship between things is as important as the actual thing itself. So you can think about these things as trying to model, say, like a family hierarchy, right? And it's not necessarily that you just have different people, but really like that interaction between the people of, let's say, is related to, or is the uncle, or is the father, and so on, right? That relationship is itself a piece of the data, and that's where you get the graph kind of idea and graph kind of data sets. And these are like obviously big in social media, figuring out like different links between different people, recommending your friend set, like if you have like, did you know these people? Again, that's really based on sort of a graphical data set, and being able to predict those kind of relationships and being able to orient that relationship as sort of as important as the data itself and the data components itself. So those are the really 5 major components or 5 major data modalities that exist out there. Again, millions of use cases for each of those in each industry and each field. The last major component of AI and how it works is really how the models and how the algorithms learn from the data. So we have the algorithms that we talked about, the data sets and the data modalities, but like how does it actually learn patterns from the data? So there's really 3 major categories of that. The first one is supervised learning, and basically a way for us to oversee like teaching the algorithm patterns. So in the house price example, you think about things like you have historic examples of the feature set, say, of houses, square footage, those kind of things, and you map it to historic values of house sales. And so you have historically labeled samples that allow you to map that input to output. So no longer do we have an idea of what's there and like historic evidence for what's there, but really we're starting to look for outliers to patterns. So these are applications where you can think about like anomaly detection or fraud detection, where you're thinking about things like, oh, this looks like it's a 3 sigma outlier, those kind of ideas. Those are really unsupervised in that it's learning the patterns from the data, but you don't really know what's there and what's out there. You just know that this is slightly different, slightly anomalous from other things, right? Within that category is also clustering and segmentation. Again, in fields like, say, retail and consumer products, like customer segmentation, grouping people into similar cohorts, very important aspect. But being able to do that and being able to group them, again, you don't really need to know what the groups are. These algorithms will be able to learn the patterns, be able to like group them coherently into groups of people that look similar. And then it's on us afterwards to basically impose and impart some meaning to those groupings. And the third one is becoming bigger and bigger these days, is reinforcement learning. So this is the last real major way that algorithms can learn. And it's really geared towards robotics and has become more and more a big deal within the generative AI space. So reinforcement learning is really to do with algorithms and models that are able to interact with an environment and learn from them. So you can think about a robot trying to navigate a maze. It doesn't know exactly what the universe looks like, it doesn't know what the maze output looks like, but it's reacting to it. It's doing like movements from left to right, and then detecting there's a wall there, and then from there making a further inference and further like decision making on that part. In that sense, it's more of a niche area right now, although it is becoming bigger and bigger in that as algorithms get more sophisticated beyond supervised, like with labels, unsupervised, just more density-based approaches, we are now getting into a phase where we're learning from the environment, where the environment itself may be a little bit ambiguous, and learning from like the universe of possibilities. So those are the three major components of how AI solutions and how AI is built from. So again, just to repeat, it is really the algorithms and the sophistication of AI, the level of AI, the data modalities that are the algorithms learning from, and really how it's learning. So those three are really the core crux of what is AI and how it works. Just to give you a few examples, I wanted to talk about one example and a couple modalities, and just to give you a sense of like how these things actually play about in use cases, and how people are using these systems and using these tools to develop solutions that bring value. So the first example I'll cover is to do with more text-based analysis and trying to extract keywords and key topics and key trends from like hundreds of thousands of legal documents. What basically happened was this company came along and has hundreds of thousands of contractual documents that are basically things like house price or house sales. So they have like the owner, the seller, the buyer, the lending bank, the quantity it was sold at, the dates that people purchased at, like a lot of the like historic financial information that are related to anything house related and house insurance related. These 100,000 documents every year need to be manually analyzed by sort of human reviewers. And historically what happened is they extracted the key terms like the house price or who was the buyer, who was the seller, by hand with a fleet of basically humans on the back end. And so these contracts, which were typically very, very, like maybe faxes of photocopies of photocopies, and being able to extract like manually one at a time these numbers. And it costs hundreds of thousands of dollars every time they have to go through this, millions of dollars over the course of a year. And so being able to automate this with AI was obviously one of the big value adds that we could do. The second example I want to talk about is diabetic wound management. So this is an application in healthcare where if you're diabetic, you have a high susceptibility to bad circulation. And one of the major things you need to do is you have to keep moving and you have to keep mobile. So what we designed for one of our clients was basically being able to automatically monitor people's movements and be able to define what they're doing using some gyroscopes that are on a sensor. So it tried to do basically what a lot of these healthcare apps are doing, and try to like define exactly the movement type that you're doing. So you could be walking or running, or you could be sitting or idle. So those kind of like classifications, again, was one of the major components of trying to tame a lot of this raw gyroscopic movement. The data set that's coming out is like ones and zeros into something that is more like in this 30 seconds you were sitting, in this 2 minutes you were walking, those kind of ideas, right? To like monitor the patients over time. And so in this case, what happened was again a supervised approach where we had historic patients wearing the sensors, and they annotated basically what they were doing at the time, the activities that they were doing. Our algorithms were basically trained on this historic data set to map these sequences of movements and these patterns in like some of the gyroscopic movements into what actually the labels were doing, and like actually what they were doing is sitting or standing or whatnot. Right? So one of the added complexities that we added here was to add an unsupervised learning approach. So we had set classes of people's movements going upstairs, downstairs, jogging and walking, or sitting and lying down. And we also added an unsupervised class where basically if it didn't fit within those categories, if the basically sequence of events and the gyroscopic data, it didn't look like it fit within those categories that we predefined, it would label them for human review afterwards, and also maybe signal to the healthcare provider that maybe someone fell over or there is some issue there that we should look at in the data. The last use case I'll mention is towards the image data modality, where we were looking at large-scale buildings and infrastructure. So these were typically power plants, and there's also bridges and roads and these kind of things. And historically what happens is a human investigator has to go to these sites and basically look at the buildings and like do an inspection around them to see structural defects, and like say there's a crack in the bridge or there's like some spalling in the concrete or what have you. And so this was a very human-intensive task that also took a lot of human SME time. And this is very expensive, obviously, you have to do it, and it's a very manual process. Historically, these human engineers would go to the site, they would fly a drone around actually, and basically record the video around the buildings and the structures, and take that offline, analyze the video, download it, take several days to come back, and then it's like, oh, there might be some impact here, and then they have to go back on site and then define, and then maybe like zoom into that category of like, or zoom into that area on the building, right? And again, very human intensive, very long, and took like days and weeks of time for something that we can automate. So the solution here ended up being we applied computer vision models. So these were traditional image-based models that mapped patterns in the images to like human labeled defects in buildings. So like cracks and spalling and what have you. So a lot of these are just basically human annotated, and like here's like a crack on the building or whatnot. And so from those, we built those models and we deployed them onto the drone. So these were now basically running in real time that allowed you to like automatically say, there's a defect here, let's zoom in. And so that the human engineer, instead of having to like, take the video offline, download it, and then analyze it, could basically just zoom in real time and basically highlight the defects in the building and basically quantify some of the issues that were there. So I just mentioned 3 examples of different use cases that we've solved historically that are really applicable to the wide range of applications out there. Across all data modalities, it really is, from the AI space, more of an agnostic tool and agnostic solutions that we can build. So these types of solutions that can analyze images from houses or buildings and cracks and piping are the same type of solutions, same type of models that are really being used in, say, healthcare to like detect tumors and track cancer in CAT scans or radiographic scans. So again, these solutions are use case specific, but the types of technologies and types of approaches are very, very similar across industries. So a text-based solution to extract entities can be applicable in the legal space, in the retail space, in the financial space. Again, with the signal processing time series, you can have forecasting in supply chain, you can have forecasting in stock prices. Again, from the technology side of things, the solutions and AI capabilities are very, very similar, and you can just lift and shift a lot of that paradigm into any different areas and any different use cases. So hopefully I've given you a sense of what is AI and what it can do, and some of the examples of use cases that we've solved. I wanted to conclude the section with what is the future of AI. And so nowadays you hear about Gen AI and large language models and generative models that allow you to generate text and generate images. So that field is obviously exploding, and I just wanted to disambiguate a little bit what that is and also the capabilities and where we are. A lot of traditional AI, so the machine learning and deep learning for the last 5 to 10 years, have been geared towards discriminative models, where we're trying to learn the difference between different things. Generative AI, on the other hand, is really modeling the dataset as it is. So that's really differentiating between how discriminative models historically worked and sort of the new age generative models of like learning holistically the dataset and learning the patterns so well that you be able to model the dataset itself first. And this is how you can build new documents or new reports or new images, right? Because you have such a deep understanding of that data. And the use cases of Gen AI is obviously, again, to be seen right now. Hopefully most of you guys are using Gen AI tools and to augment some of your workflows. But you can think about things beyond, say, automating your email generation or ability to code faster, right? Being able to tab complete a lot of your code sections. Generative AI can do much more than that. The easy examples hopefully you've seen already. Beyond the simplest use cases of generating content, generating text, and generating images, we can also generate more novel different data paradigms. So over the last 12, 24 months, there's been huge developments in generative AI, but also in traditional AI. There's a lot of interest and development work that's been driven by this interest from businesses and from companies, like finally being able to see a lot of the value that these technologies can bring. Again, the pace of development is massive and enormous. If you look back maybe 12 months ago and 24 months ago even, the images that were generated by an image generator looked, obviously computer generated. But nowadays, in the last 3 to 6 months, like the abilities of these models to generate text, images, code, audio, music, all of these things have advanced so far, really is indistinguishable to actual reality and actual human-generated content. And we're getting to a stage again where we're starting to pass that Turing test of artificial intelligence, where we can call things artificially intelligent. So beyond the more advanced versions of generative AI, from 2D to 3D modeling, you can think about the next generation of chatbots. And beyond what's currently out there of like this normal human text interaction between us and a computer, you can now think of things of going one step further beyond that. And the step further beyond that is the chatbots themselves being able to call tools and be able to interact with an environment. So bringing in some of that reinforcement learning that we talked about, being able to interact with a wider space rather than just generating content from scratch. And so the idea here is really being able to allow the algorithms and models to learn which tools to use, which APIs to call, whether or not to call a calculator rather than try to infer and generate that text. Being able to do an internet search for you and then bring that back and then do something else on top of that without a human having to add intermediate steps. Being able to interact with the environment is the next wave of the chatbots that we see today. And in terms of what this is called sort of agents-based system, where we're using the large language models, the chatbots themselves, to act as sort of orchestration layers between different tools that, in generative AI, things that are like predictive or forecasting is not really the core strength of generating content. And so by leveraging the generative AI component, the chatbot itself, as sort of like an orchestrator, you can basically do more and more complex second and third order reasoning tasks by calling in things like a calculator, for example, where a chatbot might not be very good at being able to perform raw calculations, but being able to call directly a calculator, being able to get that output and then ingest it back and then do something more intelligent with it. And so now we're getting to that stage of like more autonomous logic and reasoning, orchestrated again by a lot of the technologies that already exist. And then finally, I'd like to end on sort of like the outlook of what the next 6 to 12 months look like. And looking back at the last 12, 24 months, if you look at some of these graphics from 12, 24 months ago, it's obvious that these were computer generated. And as you progress, and then nowadays in the last 2 or 3 months, you can get videos that are very photorealistic and ability to generate this content. And we're at a stage where we definitely passed the Turing test at this point, where we can't distinguish between human and computer generated content. And over the next 3 to 6 months, I think we're going to start pushing the envelope of what is possible out there with a lot of these Gen AI and AI solutions that are being developed right now. I think what I find truly exciting is that the rate of progress is so vast that we are really just at the cusp and at the beginning of the journey of like where AI and Gen AI can play. The democratization of generative AI with the recent chatbots and chatbot releases have allowed for a lot more accessibility to everybody that allows more ideas and more interest to be developed. And I think that just furthers the field and furthers the moment in history where it's like the perfect time to get into the field and be able to be part of the thought process of like where these solutions go and how we develop them and what their purpose is. I personally have mixed feelings about the situation of like being able to democratize a lot of this technology. I spent my whole career learning and developing the solutions and learning the nitty-gritty, allowing the democratization, like being able to use these tools and that learning curve, really being eased up for everyone is tremendously valuable for everyone else, I think, and great for society as a whole. Just personally, it's just a bit hurtful that, last 10 years of my life may not be as useful as the next.